So, hi everyone. I hope remotely you can hear me. So today it's a pleasure to introduce you Florent Renaud, who is coming from Lund Observatory in Sweden. So Florent used to do his PhD in Strasbourg in France. Then he moved for a PhD, for a postdoc, sorry, in Paris-Saclay. And after that, he moved in the UK in Surrey, where he did a postdoc. And Florent moved in Lund a couple of years ago, and he's not in a permanent position with probably such time, but with, as he was telling me, volunteering teaching time as well. So yeah, so Florent is well known for all his high resolution hydro simulations, especially of local galaxies, in different also gravitational framework. And so yeah, so today Florent is going to speak about what happened to the Milky Way 8 billion years ago. So Florent, the floor is yours.
Thanks a lot, Guillaume. Thanks very much for having me here and for dealing with all the paperwork in the organization. It's such a great pleasure to talk live to a live audience, not to my screen. I'm so happy to see a good fraction of your faces in the room, and hi to the people also listening on Zoom. So yeah, I'm gonna tell you today about some clues about what happened to the Milky Way about 8 billion years ago. And of course, this is not my own work only. It's a team effort. And I would like to emphasize the contribution from the team members, in particular the students. So Flor van der Klaar was doing a master student in Lund, and she's now a PhD student in Zurich. And Timmy, sorry, I still cannot pronounce his name, was also in Lund for his master thesis and is now working as a PhD student in Stockholm. My partner in crime in Lund is Oscar Gertz, and our godfather, I would say, is Alessandro Romeo from Chalmers University. Of course, also a huge contribution from the Wintergatan team. So Justin Reed in Surrey in the UK, and everybody else in Lund. So Niels Reide, Eric Andersson, Thomas Bensby, Martin Rey, and Diane Feuillet. Many thanks to them. What I'm going to show you today is mostly their work. So let's start with a bit of warming up. Talking about chemical enrichment, everything you know about chemical enrichment to understand this talk, and basically everything I know about chemical enrichment. If I represent the arrow of time, and I said that t equals 0 corresponds to the epoch of star formation, is where the gas is converted into stars, and this is where the stars inherit the chemical properties of the clouds in which they are born. After some time, because of stellar evolution, the most massive stars will explode as type 2 supernovae. And what I care about in this process is that they will release the alpha elements, so the products of the fusion of helium-4, so in particular oxygen. So this could happen as early as 3 million years after star formation, and as late as 40 million years. But on average, it's roughly 10 million years of star formation. And then later, at a time which is quite difficult to assess, we have the other big families of supernovae, type 1a supernovae, you know, the one that come when you have a mass transfer in a binary system. And what I care about from these supernovae is that they will release heavier elements, in particular Fe, so iron. The time scale for this is not fully understood, it's not fully quantified, but basically what we care about is that typically it's much larger than 10 million, which means that in this small packet of the galaxy, of the universe, the chemical composition evolves with time. I start with something which is, you know, my reference point, so not enriched, and then the medium become enriched in alpha elements, and finally in both alpha and Fe elements. And this is very important because this medium is what will be used to form the next generation of stars. And therefore, that tells me that the chemical composition of stars can tell us about the formation history of the galaxies, if we look at them. This is what has been done millions of times almost. So here I'm going to be a bit Lund-centric, showing the work by Thomas Bensby. When here every dot is a star, it plots here as a function of metallicity on the x-axis and the abundance ratio alpha over Fe on the y-axis. Many other people have done that, and they all report that in the Milky Way, we basically have a sequence up there with high alpha over Fe stars, which correspond to stars in a thick disk, which are chemically hot and usually old. When I mean old in that case, I mean more than 10 billion years. So a thick disk, and down there we have this low alpha over Phi sequence corresponding to a thin disk, thinner but radially more extended, kinematically colder, so lower velocity dispersion, and made of younger stars. And here in between, somehow, we have a bit of a mess made of stars you can see in the halo, maybe connected to the accretion of satellites from external origin, with also the presence of globular clusters. Some of these systems have streams, but that's a full different seminars to talk about that. And you see that in the chemical space, the kind maybe connect to the thin disk in this way. It's not totally understood yet. So to complete the picture of the Milky Way, let me add a bulge at the center, and that's it. That's my artistic rendition of the Milky Way. Clearly, I'm not an artist. People have done that much better than I do. This is an artistic rendition, much better looking, actually quite accurate. In case you're lost already, you are here, something like 8.5 kiloparsecs away from the center. You see the bar with an angle of about 20 degrees. And I can use this example, what we think the Milky Way look like, to make my guess about the question I ask. What does the Milky Way look like 8 billion years ago? So to make this guess, I'm going to use state-of-the-art tools in astrophysics, and I'm going to use my knowledge of galaxy evolution. I know that before the galaxies were forming more stars, their star population were younger, and therefore the galaxies were bluer. I make them blue. And I know also that these galaxies grow inside out. So before, they were probably smaller, 8 billion years ago. And now if I want to compare this guess of what the Milky Way looked like 8 billion years ago to observation of galaxies at this redshift, at this look-back time, I have to degrade the resolution. So that's it. That's my guess. 8 billion years ago, the Milky Way looked like that. Well, it's a bit simplistic, probably. Let's agree on that. We can compare this to what galaxies look like at this redshift, in particular the observation of Debbie and McGreen. You see here. So in terms of color, I'm not so far. In terms of size, still okay. In terms of structure, it's total catastrophe. I don't have this centrally peaked structure. I don't have the spiral arm, the bar anymore. I see this mess, these clumps of gas. The clumps really dominate the morphology, in particular in the ultraviolet. So these galaxies are actually very important and make their own class of galaxies called the Clumpy disk galaxies. And we think that most of these galaxies at redshift 1, 2 have huge star-forming clumps like those, several of them. To give you an order of magnitude, this could be as big as 10 to the 8, 10 to the 9 solar masses. So as big as dwarf galaxies. But you have several of them in each of the disks. And as I said, they dominate in UV, so they form stars. And we can compare these star formation regions to star forming regions in local galaxies, in contemporary disks, like this one, for example. And they have things in common. They do share similarities in a sense that they form stars in a secular way, in a steady state, in a quiet way, which means that these two classes of galaxies are part of the main sequence of galaxy evolution. That's where most of the stars are formed in this steady state mode. But we can also compare these star forming regions to the fireworks of star formation when it's the most violent, the most intense. Like we have here in the starbursting galaxies, like in interacting galaxies and mergers, in the example here, the antenna galaxies. And a star forming region here and a star forming region there also share similarities in the sense that they have a high surface density of gas, a high star formation rate, and they have high level of turbulence, much higher than this, like at least 10 times, several 10 times higher than that. So it seems a bit contradictory that a star forming region can be at the same time secular, steady mode, and also very similar to the most violent star formation events. So to try to solve this contradiction, let me gather some clues of what's going on. First clue is that these clumps are found in disk galaxies with a high gas fraction, the mass of gas divided by the total baryonic mass, gas plus stars. So high gas fraction. I also know that the gas fraction in disk evolve with redshift. You can see this illustrated by Amit Santonge with the molecular gas fraction. It was much higher at high redshift. So in the end, and with surveys of these galaxies, we think that most, if not all, the Milky Way-like galaxies have had a clumpy phase 8-10 billion years ago at redshift 1 or 2. And from that, we can complement these studies with simulation, and we have learned many things. I just mentioned a few here. The clumps have an important role on the process of galaxy evolution. They can migrate toward the center, participate in the formation of the bulge. They can also play a role on chemical enrichment. We'll come back to that in a second. And they can also participate in the formation of the thick disk. We'll also come back to that in a second. So all these giant clumps, how do they relate to the local molecular cloud that we know and love, that we understand much better because we can observe them with much higher level of details? So that's the questions ultimately that I want to answer. To do that, what we have done is a series of control experiments. Every simulation is an experiment. And in that case, it's very controlled because you're going to see I'm playing with only one parameter. So we run this suite of isolated disk galaxies, no cosmological context, no mergers, no accretion of gas, nothing, just a disk set in isolation there. I spare you the technical details are there if you care about that. Basically, what you need to know is that we have a decent physical model to look at the global properties of the disk, the global structure. And I'm going to use this set of initial conditions, exactly the same initial conditions, changing only one parameter, which is gas fraction. The example you have been staring at, it's 10% gas fraction. And I also made a 25% and 40% gas fraction. And just with these simple movies of the gas density, you can see that the gas fraction plays an important role on the morphology of the disks. So let's have a look at that in more detail. Here is the map of the atomic gas at 10%, molecular gas and stars. What you're seeing is the giant molecular clouds that you expect in Milky Way-like galaxy, present-day Milky Way-like galaxy, distributed in kind of spiral structures that you can clearly see in the stars. If you have good eyes, you might see some clumps, which are the young star clusters along the spiral arms. And now if I do the same at 25% gas fraction and the 40% gas fraction, you see a difference. You still have this molecular cloud, but you also have much bigger structures here, there, in the molecular gas, in the stars, and you don't really see spiral arms anymore. You still have sort of elongated structures, but they are not really symmetric. They are not, their angle is a bit weird. I wouldn't call that spiral arms. So clearly, the 10% gas fraction stands apart. Gas poor versus gas rich galaxies, because at low gas fraction, what I form in my galaxy is spiral arms. At high gas fraction, I don't form spiral arms, I form giant. So from this, I can conclude that the structure of my galaxy changes at about 20%. Yeah. Sorry, say again. It's in the simulation, so it's so the Milky Way would be around 10%. The present Milky Way would be at around 10% gas fraction. So something like this. Yes, yes, and this earlier. So from that, I can see that the structure of the gas changes at around 20%. So to be fair with you, I'm showing that it changes between 25 and 10, but we had more simulations, and I can tell you it's at about 20% that things start to change between giant clumps, high gas fraction long ago in the past, and low gas fraction and spiral structures. What we see in the difference in the morphology also happened in the kinematics. That's the work from Fleur van der Klar, Mr. Thesis. Here she plots on the x-axis the gas fraction in a galaxy simulation. On the y-axis, the velocity dispersion of stars at birth, so before any evolutionary effect, before any radial migration, any disk heating, anything like that. Every point is one simulation, and the error bars show you the scatter within the simulation. So what we have here, it's a high gas fraction. These gas-rich galaxies, which happen to be clumpy, provide a high velocity dispersion to the young stars. At birth, velocity dispersion is 25-30 km per second. But this is only true at high gas fraction. If you decrease the gas fraction, if you go below this 20%, you have a sharp drop to a much lower value there. What we have seen as a change in the morphology also happened in the kinematics. So now if we want to look a bit more to quantify these changes, we know it's mainly affecting the morphology. So let's have a look at the structure of the galaxy. The one way to quantify that is to use the power spectrum density, PSD. If you're not familiar with the concept, it's relatively simple. You take a map of your galaxy, you make a Fourier transform of this map, so 2D Fourier transform. And you're going to plot as function of scale the power carried by each of these frequency, each of this mode of the Fourier transform. So here the three lines correspond to my three gas fraction. Gas poor in blue, gas rich in red and black. Don't trust too much the extreme right. It's too close to the zone limit, so I would not believe anything there. Large scales on the left, small scales on the right. And to guide your eyes, I have some power law indexes there. What we have here is that at large scales, the galaxies are relatively similar with the same power law up there. But we have a change of the slope that happens at around 100, 200 parsec, around there. And this is not new. This is actually expected because that corresponds to the thickness, the scale height of the disk. And you can understand that if you see that at large scale, your galaxy is basically infinitely thin. You don't reserve its thickness. So the turbulence motion is only 2D in the plane. But if you go to smaller scales, then you can actually resolve the thickness of the disk, and you can capture the 3D motion of turbulence. So this results in the change of the slope of the power spectrum, like that. So this has been seen before. We retrieve that at the thickness of the scale height of our three galaxies, which is within a factor of a few the same. But what is different is between the gas poor, which is really steep, and the two gas rich, which are not exactly the same, but relatively similar, much shallower, you get a difference there. You have a divergence between the three cases. So what I'm thinking from that, and combined with what I've seen in the maps, is maybe I see a transition from a disk instability regime at large scale to something different at gas-rich case, a clump instability, and a cloud, much smaller cloud at low gas fraction. So I'm going to try to test this hypothesis. If I say disk and instability in the same sentence, the first thing that comes to mind, or the first letter that comes to mind, is Q. The Toomre Q parameter, or the Safronov version, which is what you see in textbooks like that. So kappa is the epicycle frequency, basically describing the rotation of your galaxy. Small sigma is the pressure term, so dynamical velocity dispersion. And you're going to compare this to the denominator, which is capital sigma, so surface density, which represents the gravity term. And like every stability criterion, you have stabilizing effect, rotation and pressure, versus instability versus fragmentation effect like gravity. If you derive this carefully, you have to make several assumptions on the way. One of them is that the disks are razor thin, which is unrealistic. And the disks are made on only one component, 100% stars or 100% gas, but not a mix of the two, which is also unrealistic and very unpractical for my case because the gas fraction is the one thing I'm changing. So I'm not going to use this parameter. Instead, I'm going to use another one called the Roman-Falstad parameter, which is based on the Q. So I'm going to use it like here in this sort of geometrical mean. And I'm going to use three components. So I'm going to sum over neutral gas, H1, molecular gas, sorry, atomic gas, molecular gas, and the stars. And I'm going to add some weighting terms. So without going into the mathematical details, W represent how different the component is from the most unstable component, the one driving the instabilities. And Ti is correcting for this thickness. things are not rather thin, so I need to correct for that. So I have one criterion here, which is much more realistic, much more practical than the 2-1. And I can use it in my simulation. So for example, I can make maps of this stability criteria. So low values are very unstable, large values are stable. And you can see that between the three cases, basically the minimum and the maximum, they don't really change. We have the same range of parameters, but the distribution in between the two is very, very different, have much larger areas at IQ in the gas-rich cases. So I'm not going to study these maps into much detail because I won't learn more. But instead, I'm going to look at what drives instability, which component is the most unstable one. This is what I show in this ugly looking map, I have to say. This is at this position, for example, if I'm in the yellow region, the stars are driving the instability. If I'm in this greenish thing, it's the molecular gas. And if I'm in the purple region, it's in the atomic gas. So these again are a spatial distribution, like maps. I think it's much more interesting to plot that as a function of density. So here, function of density of gas on the x-axis. I have on the y-axis the mass fraction in each regime of instability. So they sum up to 100%. And you see, for example, like here, I have something like 40% in the 60% in the stars, something like, I don't know, 30% in the molecular gas, and the rest in atomic. So what I see here at 10% gas fraction is a bit different at 25% gas fraction and 40% gas fraction. But in all cases, the stars are always the main driver of instability. Most of the things are in the yellow regime. Now, if we focus on the intermediate densities, so basically in between the clumps, in between the spiral arms, the gas takes the dominant role. Here you see it's getting higher and higher when I increase the gas fraction. It's actually the main driver of instability in this density regime. And that's very important because I would say by definition, this medium in between the clumps is what will be used for forming the next clumps. So in other words, the gas sets the formation of these clumps, of this structure. Now, if I go to even higher density, the clumps themselves or the clouds themselves within these structures, I see that the stars play again the dominant role. This decreases here. So the stars dominate the instability regime within the clumps. And the reason for that is due to feedback in these stars, which are forming in these clumps, which are forming stars. These young stars inject feedback, so they heat up the gas, they inject mechanical energy, they increase the turbulence support, and they affect the gas, but not the stars themselves because of their tiny cross section. So basically, star feedback will increase the support from the gas, but not from the stars. So that's why the instability becomes again dominated by the stars. So now if we can combine all of that, we see that there is a kind of dependence on the scale for the instability. And this is what I'm trying to show in here. On the x-axis, you get the scale. And on the y-axis, you get at the top surface density. And at the bottom, Versey dispersion. This one is for the atomic gas, H1. Every color is again a different gas fraction. We do the same for the molecular gas and for the stars. If you are like me, you don't know how to interpret that. It's quite complicated, it's quite messy. But what we see is that we have a change of the slopes of these curves as function of scale. So I'm going to write this, just a tiny bit of math. I'm going to say that the surface density, I can write it as a function of the scale L to a power law with an index A. I do the same for the velocity dispersion with a power law of index B. I plug all these things together. I solve my Euler equations for hydrodynamics and gravity, and I end up with my dispersion equation. You recognize the usual suspects. Kappa is representing the rotation. I have also the gravity term and the pressure term. And you see that I have indeed the scale dependence on the with the power law index A and B. So from this, and like every dispersion equation, if I have a solution, I describe the change between the spatial scale and the time scale, and then I see the propagation of a wave. However, if I don't have a solution, so if omega square is negative, I'm not describing a wave, I'm describing an instability. So this means that instability will be dependent on the values of A and B as function of scale. So I can map that as function of A and B. First obvious regime, I would say, is this one. When sigma square, so the velocity dispersion square, is proportional to the scale times the surface density. Scale times surface density is mass divided by radius, so it's potential energy. And sigma square, the small sigma square, is kinetic energy. When the kinetic energy is proportional to the potential energy, I have virial scaling. On top of that, I have the classical regime of Tumor instability right there and here. And I also have a regime up there when self-gravity dominates toward the small scales. Careful here, I'm not saying it dominates at small scales. I'm saying that if you consider an object at a given scale and you compress it a bit, you reduce the scale a bit, then self-gravity will become the dominant term. It's the opposite in this regime. When you do that, the same contraction, the pressure will be the one dominating. So here you see different regimes of instabilities as function of A and B, so might dependent on the scales. And you have already seen that I'm not an artist. I can tell you also that I'm not a poet because I named them A, B, C, and D. So I can use this map for the instability regime and compare that to the values I showed you before, to this plot. The first thing I try to do when making this is try to plot as function of scale the position or the motion of the galaxy in this map. And it was a mess. It was extremely difficult to read. Then I scratched my head a bit and I realized that I don't care about that. What I care is when I'm in one regime or another one. So I'm going to show it here. If I have a line, this means that at this scale, I'm in the regime A of instability. So tumor-like regime of instability, disk-driven instability regime. So you see that at large scales, for all three galaxies, I show the vertical line, I have the disk-like regime of instability at large scales. Now, if I don't have the line plotted, it's another regime. It turns out that it's always a regime D. It's not automatic, but in that case, it is regime D. The pressure dominates toward the small scales. And you see that at high gas fraction, so the red and the black curves, I have this regime, so the absence of my horizontal line at small scales, but not at low gas fraction. You see low gas fraction, so the stars are the more important. Let's have a look at the stars. In the regime A, the line goes all the way to the small scales that I can resolve in the simulation. This means that instead of forming a clump or clumps, I form spirals. I form something galactic-wide, so spiral arms. And this is exactly what I wanted to explain with the difference in morphology. So all this matters for the morphology. We have seen it also matters for the kinematics, and it also matters in terms of chemistry, in terms of chemical enrichment. This is a work by Clark and collaborators. When they show here in the same plot I showed you before, so metasticity alpha over phi here, the color of the points correspond to the surface density of star formation rate. So basically, if my galaxy is forming stars fast in a vigorous way, I'm in this greenish region, so high alpha over phi. And if the star formation is much slower, then I'm in this pink, cyan, whatever color this is, low alpha over phi regime. The rapid vigorous star formation within the clumps leads to high alpha over phi. The same has been seen by other groups, like the one by Sergei Koperskov in Paris, Paola Di Matteo. They found that you can actually retrieve a bimodality in chemistry, so two sequences, high alpha over phi, low alpha over phi, again by changing the rate of star formation, the speed of star formation. So combined to what I've said before, the transition from the clumps instability to the regimes of spirals corresponds to a transition from high to low alpha over phi. So change in morphology, in kinematics, and in chemical composition of the stars. So to summarize this part of the talk, I showed you the result presented in this series of papers. We have 3, some more are coming, from giant clumps to clouds. I've told you that what happened to the Milky Way 8 billion years ago is the gas plays a less and less important role in setting the disk dynamics. The gas fraction decreases below 20%. The regime of instability shifts from clumps dominated to spiral structure, so disk dominated. The star formation activity calms down, you lower your star formation rate. So basically, you go from a thick disk to a thin disk, kinematically hot, high velocity dispersion, to kinetically cold, and high alpha over Fe to low alpha over Fe. On top of that, if you don't have massive clumps, maybe that's also when you stop forming massive star clusters. But that's again another topic. So all this has been found with simulation of isolated galaxies. But clearly the Milky Way is not isolated. So what happens if we consider the rest of the universe? Well, there is no really consensus in the community from the simulation point of view on what happens if you look at this in cosmological simulations. So in this example from the Eagle simulation, or also the Fire group have found the same. You don't really see a chemical bimodality in their simulation of galaxies. You just see something like that. In the there are a few cases of bimodality, but they're extremely rare. So this group, I found them not likely. However, you have seen bimodality in other different simulations. For example, the one by Robert Grant with the Auriga suite of simulations shown here. You see a bimodality in chemistry. Also, the work with the magic simulation by Brooks et al. That did found bimodality, not in all cases, but in several of them. And they explain this bimodality by 2 distinct episodes of gas accretion. So no consensus. Is there no bimodality or bimodality when you take into account the cosmological context? Well, this is when in Lund we apply the Swedish approach. So if I ask you what the most well-known Swedish thing, you're going to say ABBA, meatballs, Volvo cars, or maybe IKEA. And we are going to use IKEA, obviously. So what we care about is a complex system made of several components, and we try to understand how these components fit together. So I'm doing simulations. I make a simplified version of this system. I'm going to make a model out of that. And with this simplification, I'm going to be able to dissect it step by step to see how the things fit together and how the full system has assembled to make the entire object. So this is simplifying the reality, which in my opinion should be the goal of every simulation. There is no point of reproducing reality. If you are interested in reproducing reality, go to a telescope. Simulations are here to simplify reality, to make it easier to understand. Easier is not always easy enough. We can still look quite puzzled with this. But basically applying this system, this approach to the Milky Way in cosmological context in Lund, with Oscar Gertz, we came up with a Wintergatan simulation presented in a series of 3 papers here. So it's a cosmological zoom-in simulation of a Milky Way-like galaxies at 20 parsec resolution. Very similar physics and models of what I've showed you before. It includes all the cosmological aspects, including the last major merger that you've seen right now. And you see the disk forming, etc., etc. The full movies last 3 minutes, so I will not play it totally. I'm going to skip that to the question of interest. Do we have a bimodality in Wintergatan? Yes, we have bimodality. You see it forming here at the evolved age of the star. So you start up there and you form the bimodality. So this is when I have to make my disclaimer. In this simulation, alpha is oxygen. We only trace oxygen and iron. Now we have a much bigger network of chemical elements, basically the entire periodic table, but back then we only had oxygen. Of course, and like any simulation work, we suffer from uncertainties on the yields of chemical elements, on the solar abundances that we need to normalize this, on the binary fraction of stars, basically on the type 1a supernova rates, etc., etc. So this means that we have a lot of uncertainties in the chemical abundances. In the end, our Fe over h found in the simulation is kind of okay. Alpha over Fe is too high, something like 0.2, maybe 0.3 dex too high. So of course, we could say we're going to normalize the simulation results, change, for example, the solar abundances or things like that. We have uncertainties on this. So we can play a bit with this, moving the distribution up and down. But we decided not to do that because maybe in a few years, the observations themselves will have changed their reference values. So we kept the raw data from the simulation. And we say we're not going to use quantitative values, but look at the qualitative differences between the structures. So doing that and using this movie, I can already say that the bimolarity in chemistry arises at redshift about 1, which corresponds shortly after the end of the last major merger. So what do we have there? We have accretion of gas, new fuel for star formation. Let's think a bit about that. When we have accretion in this plot, what do we have? Let's say the Milky Way or your galaxy has been evolving along this track with some dispersion, obviously, and reach this point. And then at this point, you accrete fresh gas. If you talk to people doing chemical evolution model, for example, the 2-in-4 model, they will tell you that your interstellar medium will be diluted by this fresh gas, and then you will form stars. So you reduce the metallicity, and then you form stars that will pollute the gas and make this kind of loop shape. That's what is put in these models, and that works well in explaining the observed trends. But what I'm saying is that the gas that you will accrete in these cosmological filaments is very low density. It's not at all in the density when you can form stars. It will take some time for this gas to reach this high density, so basically to go toward the dense region of the galaxy before it starts to form stars. And in this process, it will mix with the interstellar medium, and the metallicity won't be so low in the end. What I'm saying instead is that I need mergers to trigger the starburst, to trigger an episode of star formation. What do I mean by that? Well, starburst, the definition of starburst is an episode of short depletion time, the mass of gas divided by a star formation rate. Careful, it's not the same as a high star formation rate. Remember, in the Clumpy galaxies, for example, you have a high star formation rate, but in a steady state, not bursty at all. So starburst is not that. Short depletion time, so a short time scale for star formation. And that's really cool because I can compare this time scale to other time scales in my galaxies, in particular, the one from chemical enrichment in Fe. In a starburst, I can form stars faster than the galaxy self-enriches in Fe. What does it mean? This means that I'm producing a lot of stars, I'm producing a lot of core collapse supernovae, so massive stars. I increase the alpha abundance in the gas, while I maintain Fe constant because the type 1a supernovae have not kicked in yet. So I keep doing this, and in the end, I temporarily boost the alpha over Fe ratio. At some point, of course, the type 1a will increase the content of Fe and will reduce the alpha over Fe content. So my prediction from this reasoning is that instead of having this loop shape, I will have a hook shape, a little spur like that. I will first boost the alpha over Fe, and then the type 1a will kick in and reduce the ratio. So this means that if we look at the simulation itself, like this, every point represents a star formation event. Not all of them are shown for clarity, but the color of the point codes the depletion time. So short depletion time, rapid star formation in purple-ish, and slow star formation, kind of boring star formation in yellowish. So let's do it step by step. We start here at low metallicity. Here, the Milky Way is a tiny dwarf galaxy. It's not, the disk is not in place yet. It does not respond to interaction and mergers, so no starburst. Steady star formation, nothing bursty. All this will be presented in a paper by Álvaro Segovia Otero in a few weeks. Then what happens? The disk starts to be in place. And when you throw a galaxy at the Milky Way, you trigger a merger and a starburst. You have these little hooks, these little spurs that I was mentioning before. This, maybe one here also. So you see the response of the galaxy to mergers. After the end of the merger phase, you don't have that anymore. You don't have the global trigger, the global stimulus for starburst. So you see a little local starburst, mini starburst, for example, passage of spiral arms, these kind of things, but nothing global. So you get back to long depletion time, quiet, steady star formation. All these things put together mean that at the end of the merger phase, after the last major merger, I don't have starburst anymore. Therefore, I don't boost my alpha over Fe. I don't make disperse anymore. And therefore, I allow my galaxy to go to the low alpha over Fe sequence. I don't lower the alpha over Fe, but I don't jump up there anymore. So it's allowed to go down. So if I put things together, in the first part of the talk, we have looked at internal or intrinsic evolution. And I told you that you decrease the gas fraction with time. So you change the stability regime. You end the clumpy phase. You move to a spiral regime. And you slow down star formation. Second part of the talk, in cosmological context, what you have at the end of the merger phase, no more tidal excitation. You don't throw galaxies at each other anymore. So you lower the turbulence. No more starburst, and no more boosted alpha over Fe. So all these things do the same effect. Less turbulence, kinetically colder, thinner disk, and lower alpha over Fe. When does this happen? Well, internally, it happens when you have the transition at gas fraction about 20%. On Milky Way, we think it's around redshift 1, so about 8 billion years ago. In cosmological context, this transition happens after the last merger, when the effect of the last merger has vanished. Again, around redshift 1, about 8 billion years ago. So the same time scale with the same effects. So you see that both the internal and external effects conspire into making the same things at the same time. So of course, the next question that you have is, what if I have an early last merger or late last merger? What if these two things are not synchronized anymore? If you want to know the answer to this, you have to invite me again next year. Because we have run simulations doing exactly this, same galaxy, but late last merger or early last merger. Simulations are done. We are in the process of analyzing them, and we publish the result in spring, more or less. So see you again next year. But in the meantime, I will conclude with showing you this plot. This cartoon is the last figure of the second paper of the Wintergatan series. It summarizes basically everything that we propose for the evolution scenario of the Milky Way or Milky Way-like galaxy. And I will leave you with the list of points discussed in the paper, in the Wintergatan series, so in cosmological context, and also in the From Giant Clumps to Cloud series, so in isolated disk galaxies. So you see 6 courses meal, a lot of information to digest, I have to say. So I wish you a bon appetit, and I take questions. Thank you.
Hey, thank you very much for the very nice talk. I wanted to ask you about the first part of the talk regarding clamps and the transition between clamp dominated and not clamp dominated, let's say. So the only parameter that you change is gas fraction.
Mm-hmm.
However, I can imagine that supernova feedback might have an effect into when and how long clamps live, if they persist, and how also maybe it can change this transition, this 20% gas fraction threshold. So what are the uncertainties on the supernova feedback modeling that you have done? Can you comment on that?
Yeah, so we are doing tests with that, changing the recipes for feedback, going as bold as no supernova feedback or different efficiencies, different energies. So stay tuned for this. What my guess is, my prediction for the results is that in the giant clumps, the densities are so high that the feedback is kind of trapped. Not in the small clouds or not in the molecular clouds in present-day galaxies, but in these giant clumps, sorry, the density is so strong that you would need a huge amount of momentum to pull them apart, basically. So maybe the effect is there, but not so big. That's something we have to check.
Okay, but if I understand, so but for example, the fire simulations, they claim they don't have clouds, and
Yeah.
just is because they put a very strong supernova feedback. So you say you don't see that.
Yes.
So you really need to put it very, very, very strong.
So that's the part when we disagree with the fire, that their clumps are short-lived, and our clumps are long-lived, and they can migrate and form the bunch. So that's the difference, and as you say, it's probably due to different feedback implementation or star formation rates. We have this 100% star formation efficiency.
Thank you.
You've got constraints on your overall stellar populations and the number of stars you have, like in small galaxies. So you can constrain your overall feedback level. So you still have to regulate star formation in small things. So you've got quite good constraints on how much energy you want to put in total, but maybe not how it's broken up. That makes sense. So you must be adapting. If you've got less supernova feedback in clumps, you still have to put in energy to prevent star formation in low mass things in some other way.
Well, we don't know if star formation is regulated the same way at high redshift and low redshift. The only thing we can do is assume it's the same because we have observational constraints at low redshift, and we can extrapolate that at high redshift, but it's not fully constrained. So I would not say that star formation has to be regulated by feedback. We'd say that the input of one massive star is the same as high and low redshift. But then the result is different because my environment is different and because my star formation rate is different and maybe my IMF is different. But this I have no clue about it.
So how do you prevent star formation in low mass systems like dwarf galaxies?
Oh, sorry, I do
How do you prevent too much star formation in dwarf galaxies, for example, in your model?
That could be a dependence on metallicity, could be a dependence on dynamical effects like the galactic shear, these kind of things. I would not say that a clump is an extrapolation of a dwarf galaxy. It might be different. You might have a different gravitational potential, for example, a core or a cusp. So to me, it's not obvious. I'm not saying that I have the answer. I'm saying that we need to look at that carefully.
But you do regulate like your low mass galaxies if you just run a dwarf with the same model.
Well, some dwarf galaxies are destroyed by feedback, right?
Sorry?
They just explode because their gravitational potential is too shallow. For example, maybe that's the way you form the ultra faint dwarf galaxies because you scatter the material at large distance.
I don't think that matches self-consistent with the star formation, like the number of stars in a dwarf galaxy and its chemical properties. But anyway.
Okay.
No, I have some curiosity. The first one is that I'm not an expert on this, but according to what I know, is that the presence of alpha depleted star, I mean star with the alpha element abundance lower than solar one, has been always considered an evidence of accretion process from dwarf galaxies. There are several reviews about this. According to your scenario, the majority of alpha depleted star for metallicity larger than, let me say, minus 0.10 are actually stars that have been formed inside the Milky Way. Is correct?
At high metallicity, yes. At low metallicity, maybe not. So so in the paper, I actually have a plot of in situ versus accreted origin of the stars. Basically, I'm saying that this region, I mean here, it's mostly in situ star formation, and this probably connects to the accreted material. The exact ratio, I would not bet that the simulation is precise enough to predict it. And again, we have these uncertainties on the value of alpha. So maybe this distribution is a bit skewed compared to the real one.
And what a curiosity referred to this plot. Why you have no evidence of stars or object for metallicity below -1.5? Because we have a bunch, several objects at lower metallicity in the galaxy.
Yeah, we have some. I just cut
You just
the
cut,
plot,
okay.
yeah.
And the last point is you talk about major merger, but when you talk in your scenario about major merger, you are referring to merger of gas, because we know that currently the Milky Way is experiencing merger events. Sagittarius is a proof of this, and this impact on the star formation history of the disk and so on. So your scenario, when you talk about major event, you are referring to huge gas merger.
Yes, more or less, yes. You bring similar galaxies, basically. So you bring a galaxy which is similar to the Milky Way at a given epoch. So similar mass. When I mean major merger, I mean mass ratio close to unity. And to trigger star formation, you need indeed a wet major merger, so gas, not necessarily gas rich, but with not an elliptical.
Just a matter of the ratio between the two objects.
Yes.
Yes, I was wondering, how sensitive are your simulations to the properties of dark matter? I presume you're using some kind of CDM framework, right?
Yes.
Are they like very sensitive? Does it change the evolution significantly depending on what you assume?
I haven't looked at that, but I would bet yes. You will have probably a different galaxy mass function. You will have different merger timescales. As Guillaume mentioned, I did some simulation with MOND, particularly in interacting systems. And because you don't have dynamical friction from the halo, your interaction timescale is much longer. Maybe there is not even merger at the end, not coalescence. So that would change, I would say, everything. The timescale, the response to starburst, the enrichment, star formation rate, everything will be different. Probably the structure of the resulting galaxy also. But you would need to run the simulation to quantify that.
Okay, nice.
Thanks. Yeah, so I have also a question: is how sensitive are you to the resolution, and especially for the dispersion term? Because I guess that for the isolated galaxy, you are much more resolution than in.
Actually, not so much. The one I've showed is 12 parsec, and that's me or you, and Wintergatan in cosmological context 20 parsec. So it's really similar. It's the same numerical recipe. Now that doesn't change your question. Are we sensitive to resolution? I would say obviously. In which way is very difficult to say, because every individual process has its own dependence on resolution and scale, and the combination of different processes like star formation, feedback, etc., would have a different answer, a different effect on the resolution. So we think that the model we use is tailored to reproduce a good amount of observables at this resolution. Now, if we keep the same model with the same values and we increase the resolution by a factor of 100, it's going to be catastrophic. Trust me, I did it. And I burned so many CPU hours because I kept the wrong model at a crazy high resolution. Not published. So yes, my point basically is that every subgrid model needs to match the correct resolution. And that's really not easy to do.
No, my point is just that naively I will have thought that the resolution is at much more impact on the isolated cases than on the cosmological model. Just because when you use a merger, you don't necessarily get a big resolution with the star formation, but when you do isolated, maybe you need something.
You can. So I made a simulation of merger in the past with much higher resolution, but I changed a bit the parameters of the subgrid recipe so that I can still match the observables, for example, the Schmidt-Winnicott diagram, these kind of things. You have to be careful in doing that, but then you can still have a decently fair comparison between different models, and we see the effect of cosmological effects versus isolated systems.
So is there any other question in the room? Okay.
low metallicity, because at low metallicity you have only 0.5 that you can compare with the typical 0.4 value that you have for globular cluster in the air. But if you go, for instance, solar metallicity, you never achieve a solar scaled value with the discrepancy of about 0.3. So maybe this may be saying that you are completely underestimating the contribution coming from type 1a supernova. That I agree with you is a messy, but maybe the difference here is really too large. It's about 0.3. So it's
yeah, probably yes. I think it's what you said, and this is this become more critical when I compute the ratio of abundances, and I increase the errors basically by computing the ratio between two wrong things. When you don't see a critical difference or huge difference in if I only have FE. So yeah, I agree with you.
Yeah, so we have two questions. So Pablo, if you want to unmute yourself and ask a question.
Hello, thank you very much for the talk. I think you did not mention, or at least I don't remember, supermassive black holes and AGN in your talk. So of course you were talking about the thick disk and the thin disk, and maybe they could have a lesser effect. But in principle, I would say that they could change the properties of the gas that is falling into the galaxies, and maybe affecting the short time scale star formation and the alpha element abundances. So I don't know if you forgot about those on purpose, or what are your thoughts about the effects of AGN in this evolution that you are picturing?
Yeah, I did avoid them on purpose because we don't have AGN feedback in this simulation in any of them. Our choice for not having AGN feedback is that we think there are still too big uncertainties on the models to put an AGN feedback and make predictions. So we prefer not to put any. And what effect they would have, I would say that in terms of regulating star formation, it's really localized effect next to the galactic center. But as you say, it becomes much more important when you, in terms of gas recycling, when you eject the gas, maybe you're recycling in fountains, and you will change the chemical composition of the next generation of stars, and also the timescale for star formation. That will probably change. Maybe that would split the two sequences even more by introducing a longer time scale like that. But again, we haven't looked at that in detail.
Okay, and there was a question from Rob Grant. So same, if you can unmute and ask a question, Rob.
Yes, hello. Can you hear?
Yep. Yes, we can.
Okay, thanks for the nice talk, Florent. And as you nicely pointed out, there are quite a few different proposed scenarios now for the bimodality. And even in your own work, where you study this isolated set of galaxies and the cosmological set, you identify the massive clumps as one mechanism and the cosmological context as another. And they all seem to happen at the same time. So I was just wondering, do you think there's a chance that we can distinguish observationally which of these scenarios is correct? And if so, what's the kind of observable and information that we would need to do so?
Yeah, of course, it's a very good question, a very difficult one.
Yeah, I keep thinking about this myself.
If I want to dodge your question, yeah, there is a easy way to do that observationally. We look at another galaxy than Milky Way when the last major merger does not happen at the same epoch. But good luck resolving all this in extragalactic context. So if I stick to Milky Way, well, I don't really know if there is a clean way to separate the two scenarios.
Yeah, I was thinking for a while about ages, good stellar ages, but it seems that some more than one scenario sort of occurs at the same time, and if the disks form contemporaneously or separated in time for multiple scenarios, I think it's awkward. But
yes, I think that could be a way, but I have showed for some of these aspects the transition is relatively sharp or relatively rapid. but still, I think it's well within the bars of the stellar ages, and even with the next generation of instruments, I think it will still be not possible to distinguish the two.
Yeah,
well,
I think
I'm not very optimistic on that.
Thanks.
Jump on that. So, because we know in the Milky Way there have been really a succession of major merger with Kraken, with Galaxies, with the LMC. Can you just not see that at some point you're going to stabilize the starburst and then you reproduce a starburst, and so just see the situation, just to see the differences? But you really need to get at some point some metastatic threshold to be able to see effect.
So that's also something I'm looking at right now. Actually, I try to see, there is this idea that maybe when you have a starburst, you already have a high level of turbulence. When you throw another galaxy during the starburst, you will maybe saturate. You cannot increase the level of turbulence forever. This is something we have said in the context of Clumpy galaxy mergers. We cannot reach crazy high value of star formation rate. So for example, we cannot do sub-millimeter galaxies because of that. I'm not so convinced this is true, because physically I don't see why you should have a magic saturation ceiling for your turbulence, why it doesn't keep increasing forever. So what the way I'm testing this hypothesis now is to run interacting systems, so isolated galaxies in interaction, but 3 of them. And I do exactly this. I make the 2 interact, and then the 3rd one arrives, and see if I can boost again, starburst, even more, or if instead I'm already in excited mode and I cannot go further than that. First results show that no, I keep going and I keep make a starburst of starburst and increase the star formation rate. And so feedbacks try to regulate, so it makes really a mess in ejecting gas, etc. But the star formation rate keeps increasing, and also the chemical enrichment, etc. So all this is again question of timing and the relative importance of the different mergers.
I guess you predict a star formation rate as a function of time in your models, and I wonder if this could be one way to disentangle between the 2 scenarios that Rob was asking, because I imagine that in the case of the clumps, I mean, when you don't have a merger, the star formation rate as a function of time would be smoother. While when you have a merger, it will be a very peaked burst.
Yes.
So maybe, I mean, we can measure that in the Milky Way, and maybe this is a way to disentangle the 2 scenarios.
If you have precise enough stellar age, yes.
Well, we don't have precise enough stellar ages. What we have is precise star formation histories.
Okay.
The 2 things are different, because while it's difficult to get precise individual stellar ages, as an ensemble of the stars, you can have precise star formation histories. So we haven't.
Yeah. So if you
have seen them.
If you see a burst at redshift 1, 2,
we see a burst
yes.
10 years ago when the merger with Gaia Enceladus happens, and what we have so far is a quite big star formation burst at that time in the Milky Way. So I think this is probably a demonstration that this one effect of this burst, which, so yeah, I mean, it's something that yeah, sometimes in papers, theoretical papers, you do show the star formation rate as a function of time, but I think it's well, it's an observable that is not often considered, because there is this belief that we don't have precise enough stellar ages, but what we can have is precise enough star formation history, that at least if you use the right technique, as we do.
Okay. I would be happy to talk more about that.
I work with stellar models, so I think that this point that the stellar age are not correct is a little bit, let me say, a legend, in the sense that, of course, stellar models have a huge uncertainty. But when if you want to determine the age of a single star, the uncertainty can be 20, 30%, maybe larger. But when you face with a bunch of stars, very large ensemble of stars, you can achieve a very good accuracy. We are able to measure the age of globular cluster with an uncertainty of 0.4, 0.5 billion years. That is a good resolution if you compare with the age. And the same happen when we apply this to a large sample of stars as the one provided by Gaia, and so something that should be reconsidered at least. I'm not saying that model have no uncertainty, stellar model, but in any case, it's not so dramatic, let me say.
Okay. Thank you. Thank you.